Every 175 years, the outer gas giants align, creating the most direct and energetically efficient route from Earth to each planet. In the mid-1960s, the discovery of a rare opportunity for exploration between 1976 and 1978 prompted the planning of an extensive tour of the outer planets and their moons, which became known as the Voyager mission. By the time the Voyager spacecraft were launched in the summer of 1977, budget constraints necessitated a reduction of the Grand Tour to an exploration solely of the Jovian and Saturnian systems. Nonetheless, they initiated the launch of Voyager 2 on a course facilitating travel to Uranus and Neptune. Following the remarkable success of Voyager 1 and 2 in uncovering the marvels of Jupiter and its 4 unique moons, as well as Saturn, with its stunning rings and mysterious moon, Triton funding was allocated to redirect Voyager 2 towards the outer gas giants, thereby reinstating the initial Grand Tour plan. Subsequent to its nearest encounter with Saturn, on 25 August 1981, the spacecraft's trajectory was modified to direct it towards Uranus and Neptune. 8 years later, Voyager 2 achieved its nearest proximity to Neptune and its most significant moon, Triton. The majority of our understanding regarding those two entities is derived from that encounter. No spacecraft has ever explored Pluto and its co-rotating companion, Charon. However, terrestrial observations have yielded ample data to prepare for their inaugural encounter with the robotic probe, New Horizons, set to arrive in 2015. Currently, the evidence suggests that the Pluto-Charon system and Triton are interlopers, originating from a region beyond Neptune's orbit. Initially categorized as a planetary pair due to their orbit around the Sun, Pluto and Charon were reclassified as dwarf planets in 2006, following the discovery of larger asteroids also orbiting the Sun. Triton likely originated from a comparable population of dwarf planets, although it is technically classified as a moon, after being captured by its adoptive parent, Neptune. The formation of the solar system was an unfinished process. At this juncture, 4.5 billion years into its existence, the solar system has coalesced into a sun and 8 planets. Yet remnants of its primordial, formative stages persist unassimilated. The initial phases of accretion involved the progressive aggregation of dust and gas into particles, boulders, and sufficiently large entities now referred to as asteroids. The largest asteroids increased in size by attracting smaller ones into their gravitational fields, ultimately resulting in the formation of planetesimals. Within the inner solar system, 4 planetesimals would generate the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. In the outer solar system, 4 substantial rocky planetesimals accumulated sufficient gases from the Sun's formation to evolve into the 4 gas giant planets: Jupiter, Saturn, Uranus, and Neptune. As the 8 survivors matured, they accumulated the majority of smaller asteroids within their orbits. Consequently, the relatively proximate rocky planets purged the inner solar system of the majority of its asteroids. Despite their considerable distance from one another, the gas giants possessed sufficient mass to clear the protostellar disk from within Jupiter to slightly beyond Neptune. Several asteroids and planetesimals that evolved into moons likely formed concurrently with their parent planets, as they orbit in the same direction as the rotation of their central planets and are situated approximately within the ecliptic, the flat plane encompassing the orbits of all 8 planets. The distance between Mars and Jupiter is too vast for either planet to clear the asteroids in the intervening space, resulting in a belt of unprocessed asteroids that remains in that region, potentially representing an incompletely formed planet. An alternative model posits that catastrophic collisions between fully formed planets may have subsequently generated the asteroid debris in that region, due to the absence of a sufficiently large planet beyond Neptune's orbit to incorporate them. A vast region of asteroids extends for 6 billion kilometers beyond Neptune to the periphery of the solar system. The outer band of asteroids is designated the Kuiper Belt named after Gerard Kuiper, who proposed their existence in 1951. Although the Irish astronomer Kenneth Edgeworth had presented a comparable concept 8 years prior. Asteroids with diameters of several hundred kilometers possess sufficient gravitational force to assume a spherical shape. The accretion process for bodies nearing 1,000 kilometers in diameter generates sufficient thermal energy to liquefy their interiors, resulting in differentiation into a core and mantle. In the outer solar system, where frigid temperatures allow water to adhere to mineral substrates, the mantle of asteroids contains varying quantities of water ice. Consequently, the substantial moons of the gas giants and the larger asteroids in the Kuiper belt predominantly consist of icy bodies, exhibiting densities approximately between 1.5 and 3.0, with the density of pure water being 1.0. The celestial bodies that orbit the Sun are classified as dwarf planets. Celestial bodies that revolve around other planets are classified as moons of those planets. According to formation theory, they are fundamentally identical. Asteroids, similar to stars, frequently form in pairs. Pluto and Charon serve as exemplars. As elaborated below, Triton may have previously been part of such a binary system. All three are evidently snowball worlds characteristic of those found abundantly in the Kuiper belt. Triton is classified as a moon due to its orbit around Neptune, whereas Pluto and Charon are designated as dwarf planets because they orbit the Sun. All three, however, share a common origin in the Kuiper belt, a region of asteroids and planetesimals that orbits the Sun beyond Neptune's trajectory. This outline delineates a credible account of their origins and the trajectory that led them to their present positions. 1. The protostellar cloud of gas and dust that constituted our solar system possessed a sufficient quantity of heavy elements to be deemed mineral-rich. Consequently, dust particles, rocks, and numerous boulder-sized accretions emerged as the majority of the cloud collapsed toward its gravitational center. 2. More than 99.9% of the mass of the protostellar cloud collapsed into the Sun, while the remainder dispersed into the protostellar disk. Due to either fortuitous circumstances or principles not yet comprehended, 8 planetesimals surpassed their counterparts in size, attracting all smaller objects within their orbital trajectories into their gravitational fields. The 8 full-sized planets emerged, with the 4 outer planets sufficiently distant from the Sun to preserve substantial quantities of hydrogen, helium, and other gases. 3. From the residual material of the protostellar disk, millions of smaller accretions did not coalesce into fully formed planets. Certain entities transformed into satellites orbiting planets, such as the Jovian moons and Titan. Some transformed into asteroids, orbiting the Sun within a belt situated between Mars and Jupiter, or within the expansive Kuiper belt, which extends approximately 6 billion kilometers beyond Neptune's orbit. 4. Certain asteroids attained sufficient size to generate adequate heat through radioactive decay. This, combined with the kinetic energy from repeatedly colliding with smaller bodies, resulted in the melting and separation of the interiors of these asteroids. Spherical planetesimals, possessing metallic cores and mantles of minerals and water, with diameters of approximately 1,000 kilometers or greater, have now been classified as dwarf planets. Multiple binaries, or planetary pairs, were created orbiting around a mutual center of gravity. 5. The largest known dwarf planet in the Kuiper belt is Eris, with an uncertain diameter ranging from 2,400 to 3,000 kilometers. Triton, 2,700 kilometers, and Pluto, 2,300 kilometers, given their comparable dimensions, likely originated in the Kuiper belt. Their surface temperatures were sufficiently low to condense methane and nitrogen at that distance from the Sun. 6. Objects in the Kuiper belt are periodically disturbed by the proximity of the massive planet Neptune. Some are propelled into more eccentric and oblique orbits around the Sun. This phenomenon seems to have occurred with Pluto and its smaller satellite Charon, which rotate around each other in gravitationally locked synchrony, and together orbit the Sun in an elliptical trajectory that positions them closer to the Sun than Neptune. For 20 out of their 248.6-year orbital cycle. The more massive planets have acquired additional Kuiper belt objects. This seems to have been the destiny of Triton, potentially the last remnant of a binary dwarf planet system. The nature and intricacy of the encounter propelled Triton into a retrograde, oblique, and initially eccentric orbit around Neptune. 8. Triton's interaction with Neptune likely generated sufficient energy to melt water in its mantle, while the eccentricity of its initial orbit sustained tidal heating that could have maintained liquid water for nearly 1 billion years, although the surface would have likely frozen rapidly. 9. Triton's retrograde orbit, combined with friction from debris resulting from its collision with Neptune, has led to viscoelastic tidal forces that have regularized its orbit, rendering it nearly circular. Nonetheless, radioactive decay within its core may continue to produce internal energy. 10. The circumstantial evidence supporting a familial resemblance among Pluto, Charon, and Triton encompasses their analogous bulk compositions. Possessing a density slightly exceeding 2.0, they are composed of approximately 2/3 rocky minerals and 1/3 water ice, along with other frozen gases. Both possess tenuous atmospheres predominantly composed of nitrogen that dissipates from their polar regions, which orient both towards and away from the Sun, due to their significant tilt relative to the ecliptic plane. 11th. Triton's retrograde orbit around Neptune results in gravitational drag that pulls it closer to the planet. Ultimately, Triton will approach Neptune sufficiently to be torn asunder or collide with its adoptive progenitor. Pluto and its diminutive counterpart, Charon, are a duo, likely formed simultaneously through the same process. They revolve around one another on their respective axes every 6.38 Earth days. Consequently, they consistently maintain the same demeanor towards each other. No spacecraft from Earth has visited Pluto or Charon. Thus, terrestrial observations have constituted the sole source of information regarding their characteristics. These are insufficient to discern any surface detail on Pluto. Charon is insufficiently large to discern even that extent. For the sake of simplicity, we will refer solely to Pluto, acknowledging that our statements regarding Pluto may not necessarily pertain to Charon. Pluto likely originated from the Kuiper belt, as it predominantly resides in that region during its orbital cycle. Its orbit is highly elliptical and inclined over 17 degrees relative to the plane of the other planets' orbits around the Sun. These characteristics are indicative of short-period comets, which are also believed to originate from the Kuiper belt. Pluto exhibits a 3:2 orbital resonance with Neptune and possesses a pronounced axial tilt of 122 degrees, leading to its retrograde rotation relative to Neptune and the majority of other planets. Pluto's density of 2.03 grams per cubic centimeter indicates that the dwarf planet is composed of approximately 70% rock and 30% water ice. The surface exhibits highly reflective bright areas, indicative of frost or ice, alongside darker regions, suggesting significant topographical heterogeneity. Pluto exhibits the second highest level of surface contrast in the solar system, following Saturn's moon, Iapetus. The assessment of geological activity on Pluto is unfeasible without higher resolution surface images. Spectroscopic evidence suggests that Pluto possesses a highly tenuous atmosphere primarily comprised of nitrogen, along with trace quantities of carbon monoxide and methane. The surface temperature is approximately -230 degrees Celsius. Consequently, the surface predominantly comprises nitrogen ice, with minor amounts of frozen carbon monoxide, methane, and water ice. Triton is the largest moon of Neptune and the 7th largest satellite in the solar system. It follows a nearly circular orbit around Neptune in a retrograde manner, moving contrary to the direction of Neptune's rotation. Triton's orbital plane is significantly inclined relative to the ecliptic, and as Neptune revolves around the Sun, Triton's poles alternately face the Sun, resulting in pronounced seasonal variations in the polar regions. These orbital characteristics indicate an origin distinct from Neptune's accretion. Triton possesses a density of 2.08 grams per cubic centimeter and a diameter of approximately 2,700 kilometers, both of which exceed those of Pluto, characteristic of substantial Kuiper belt objects. The majority of astronomers contend that Neptune acquired Triton from the Kuiper belt. A plausible model suggests that Triton may have originated as part of a dwarf planet pair, subsequently engaging in a vigorous interaction with Neptune that resulted in the separation of its companion. Triton's dimensions and density indicate a composition comprising approximately 2/3 to 3/4 rocky material, with the remainder consisting of water ice and other frozen gases. Delicate yellow to peach-colored tones on its surface indicate the existence of organic compounds, potentially reaction products from methane, too. The blue-green regions near the equator may indicate the presence of frost or ice composed of nitrogen and nitriles. Triton's surface is the coldest recorded in the solar system, at -235 degrees Celsius. At this temperature, molecular nitrogen, N2, hydrocarbons and nitriles all condense. The surface is believed to comprise frozen nitrogen, water, and carbon dioxide, listed in order of prevalence, along with minor amounts of methane, carbon monoxide, and potentially ammonia. Triton possesses a sparse atmosphere primarily consisting of nitrogen and methane. A tenuous haze extends 5 to 10 kilometers above the surface, and indications of airflow are observable in streaks of dark material expelled from geysers. In the upper atmosphere, organic compounds are produced from methane and nitrogen by high-energy particles originating from Neptune's magnetosphere, 3. While some must ascend to the surface, specialists contend that their lifespans are short. Triton exhibits a relatively smooth yet diverse topography, featuring some characteristics found on other celestial bodies and others unique to itself. Triton's significant axial tilt causes its poles to orient almost directly towards the Sun in summer and away from it in winter. During its encounter with Voyager, Triton's south pole was oriented toward the Sun, and the pronounced disparity between the polar and equatorial regions may have resulted from that seasonal alignment. The southern polar region exhibits a substrate ranging from pink to peach, adorned with a mottled white overlay. Grey streaks extend consistently toward the east. These are regarded as debris ejected from the interior by geysers, likely erupting when persistent sunlight heats the colored material beneath the translucent layer of frozen nitrogen on the surface. Nitrogen and particulate matter are emitted from fumarole-like openings, reaching altitudes of 8 kilometers and subsequently being transported downwind for distances of up to 150 kilometers. 3 prominent patches are observable at the northeastern boundary of the South Polar region, near the eastern horizon. A detailed examination of this region indicates that they are consistently dark formations, potentially basins, bordered by white substance, likely nitrogen frost. The largest area in the lower right measures approximately 200 by 100 kilometers, comparable to the size of New Jersey. They resemble lag deposits from arid lakes on Earth, yet are otherwise distinctive. The significance of their presence at the transition from polar to equatorial zones remains uncertain. The cantaloupe terrain, a distinctive topographical feature not found elsewhere in the solar system, is located in the western equatorial region. The terrain is named for its similarity to cantaloupe skin. The depressions measure 30 to 40 kilometers in diameter, featuring walls several hundred meters in height. Their spacing and dimensions are excessively uniform to be classified as volcanic calderas or impact craters. The predominant theory for their formation is diaporism, which involves the upward movement of less dense material through a denser crust. The cantaloupe-like terrain of Triton is distinctive, yet it features grooves of troughs and ridges that closely resemble those found extensively on Europa and various other icy satellites. The cantaloupe terrain integrates characteristics distinctive to Triton, with processes recognized in other locations. A significant portion of Triton resembles extensive volcanic plains akin to the Moon's mare. At an elevated resolution, these regions appear highly intricate, which depicts a series of fumaroles or calderas, sharply defined ridgelines, and depressions potentially resulting from faulting and/or sapping. Extensive flat depressions resemble the aftermath of significant flooding, potentially resulting from the dissemination of lava during cryovolcanic eruptions. This perspective is supported by the observation that the surface appears relatively young, as indicated by crater counts that are 4 to 5 times lower than those on the significantly smaller moons of Uranus. The estimated youthful age of Triton's surface, ranging from 5 to 50 million years, is a principal justification for the assumption that it is currently or has recently exhibited geological activity. The overlay of recent surface features upon older ones suggests that resurfacing on Triton has been occurring for an extended period. Moreover, recent evidence of geyser eruptions during the southern summer demonstrates seasonal dynamic activity. The extensive resurfacing is enigmatic, as Triton's nearly circular orbit raises doubts about the likelihood of tidal irregularities, with Neptune supplying energy to Triton. Interactions with other Kuiper Belt objects or continuous radiogenic decay supply the energy for these eruptions. Our knowledge regarding Pluto is limited. Readers are aware that we do not hesitate to engage in informed speculation. However, we cannot provide realistic concepts when information is limited. Triton and Pluto are nearly indistinguishable in dimensions, origin, and the tilt of their rotational axes. Consequently, we will examine the conditions favorable for life on Triton, acknowledging that it may serve as an indicator for the potential existence of life on Pluto. Shortly after New Horizons reached Pluto in 2015, we will possess the data necessary to formulate informed hypotheses regarding that celestial body. We will limit our focus to our knowledge of Triton. Triton, located 30 astronomical units from the Sun, receives 1/900th of the solar intensity that reaches Earth. Even if mechanisms had developed to harness minimal light for biological functions, it appears improbable that any liquid could persist, except momentarily, sufficiently close to the surface of such a frigid planet to facilitate biological utilization. Consequently, we must explore energy sources beyond light for potential life on Triton. The potential for organic chemistry exists. Methane and certain reaction byproducts are evidently present near the surface. The transformation of methane and nitrogen into alternative organic compounds seemingly transpires in the upper atmosphere, albeit to a lesser extent than on Titan. It is uncertain whether adequate organics, in conjunction with other chemical reactants necessary for energy-yielding reactions, such as oxidation-reduction cycles, exist on Triton. Triton exhibits a certain level of chemical complexity, as suggested by its intriguing coloration. The brown substance emitted and transported downwind from geysers resembles tholins observed on Titan. It may, of course, merely be contaminated water. The conclusion regarding chemical energy sources for potential life on Triton is that they likely exist. Multiple indicators imply that geothermal energy remains active on Triton. The youthful surface, the floodplains indicative of extensive cryovolcanism, the abundance of pits, and the scarcity of calderas exhibiting frequent eruptions collectively suggest that geological activity continues to be fueled by internal heating of the Earth. Heat with bioenergetic potential may be sourced from the interior. Neptune's magnetosphere is exceedingly weak, and magnetic energy is ineffective, rendering this likely unfeasible. Nonetheless, if substantial liquid reservoirs exist beneath the surface resembling oceans, alternative forms of energy may be present, such as kinetic energy or osmotic and ionic gradients. This is a tangible possibility. Carbon is the preeminent building block for life, under numerous conditions found on almost all celestial bodies except stars. Thus, it must be regarded as the primary candidate for the components of any Triton biomolecule. Organic carbon is evidently present on Triton. Nonetheless, if any location within our solar system could potentially utilize silicon as a fundamental component for life, Triton emerges as the foremost contender. Silane compounds exhibit structural similarities to hydrocarbons, with silicon substituting for carbon. Extremely low temperatures, absence of liquid water, lack of reactive oxygen species, minimal carbon availability, solvents such as methane or methanol compatible with silanes, and elevated pressure are conditions conducive to the formation of polysilanes. 4. Triton fulfills the majority of these criteria. The subsurface, extending to an indeterminate depth, is excessively cold for pure water to exist in a liquid state. However, it is likely under significant pressure and contains various components such as ammonia, which would elevate its melting point. Additionally, temperatures are sufficiently low to liquefy methane and methanol. Oxygen is confined to frozen reserves of carbon monoxide and carbon dioxide, while other organic forms of carbon seem to be scarce. Triton possesses conditions conducive to the formation of silanes, including a frigid environment. Impacts from celestial bodies on cold planetary surfaces, and ultraviolet radiation emanating from ice-encased silicate particles. A clear drawback to the potential prevalence of silanes is that if methane is sufficiently abundant to act as a solvent, it may supply enough carbon to rival silicon. Consequently, the likelihood of silanes functioning as foundational components for potential life on Triton appears improbable. Nevertheless, our comprehension of their behavior in distinct chemical mixtures under high pressure and extremely low temperatures is inadequate to dismiss them as potential foundational elements for life on celestial bodies at the periphery of our solar system. Meteorites and other interstellar sites seldom contain silanes. However, the protostellar disk, W33A, is an exception. Consequently, a distinct set of conditions may allow silanes to convert into biomolecules. We cannot dismiss the possibility of Triton's existence in such a realm. 11th point, 5.3. Solvents for life on Triton. The potential existence of solvents that could sustain life on Triton hinges on two inquiries. The primary aspect is their chemical composition. The second consideration is whether they could exist in a liquid state in any hypothetical habitat on Triton. Water constitutes at least 25% of Triton's bulk composition. However, it must reside significantly below the surface to remain in a liquid state. Substantial evidence exists for cryovolcanism, indicating that a mixture of subterranean liquids, predominantly water, occasionally attains sufficient temperatures to erupt to the surface. Nonetheless, it remains ambiguous the proportion of the lava from cryovolcanism that consists of water versus that which comprises methane, nitrogen, or ammonia. Similar to Titan, subterranean reservoirs of liquid water ammonia may exist, but they necessitate significantly elevated temperatures -80 degrees Celsius compared to those present near Triton's surface. Liquid methane presents a more favorable option. However, the critical inquiry is whether methane can be sufficiently concentrated to create significant solvent reservoirs. Nitrogen, 1.2, presents a compelling potential. The surface of Triton is coated with frozen nitrogen at approximately -235 degrees Celsius. N2 solidifies at -210 degrees Celsius and subsequently transitions to a gaseous state at -196 degrees Celsius. Consequently, it remains in a liquid state within a limited thermal range, presumably existing at a certain depth beneath Triton's surface. The transparent layer of frozen N2 on the surface may be sufficiently thin to allow the warming of underlying colored chemicals via a greenhouse effect. If sufficient energy can be harnessed from the summer sun to generate geysers? It is plausible that there could also be enough to create small reservoirs of liquid N2. A liquid film may exist between the frozen N2 above and the frozen H2O below, or liquid N2 may be present within the layers of frozen N2. Nitrogen, in its liquid state, possesses a low dielectric constant and a zero dipole moment, rendering it a non-polar solvent, which is unsuitable for carbon-based biochemistry. That may be the solvent in which polysilanes can attain a degree of complexity and dynamic interaction. The surface temperature of Triton is excessively low, and its atmospheric pressure is insufficient for any liquid to maintain stability. 2 microhabitats and 1 principal habitat are conceivable beneath the surface. The initial microhabitat consists of minuscule water-ammonia saline ice inclusions embedded within the predominant water ice of the mantle. The temperature near the surface is insufficient for the formation of these inclusions. However, at greater depths, internal heating, elevated pressure, and the reduction of the freezing point of dissolved ammonia and solutes may generate stable liquid inclusions capable of sustaining salt-tolerant water-based, carbon-based life forms. The second microhabitat consists of thin layers of liquid N2 atop frozen N2, with a solid layer beneath which may be frozen H2O or liquid N2 incorporated within frozen N2. The seasonally activated geysers, which seem to stem from the solar heating of subsurface volatiles, indicate the liquefaction of frozen N2. Consequently, thin layers of liquid nitrogen, or liquid nitrogen inclusions, may exist. The primary habitat for life beneath Triton's surface would be the third one. Neptune probably enveloped the satellite in the remnants of the global ocean for a period following its capture. Cryovolcanism, presumably ongoing, and the cantaloupe terrain are compelling indicators that subterranean liquid water persists on Triton. The cantaloupe landscape is primarily elucidated by the dynamic activity of subsurface liquid reservoirs. The cantaloupe terrain is unparalleled in the solar system, suggesting that any resultant formations may consist of an unusual mixture of subsurface liquids. Nonetheless, considering the estimated water content in Triton's bulk composition, it is likely a predominantly water-based mixture. Triton's circular orbit generates minimal heat in the core, leading to the hypothesis that radioactive decay within the core maintains sufficiently high temperatures to melt water and induce a cryovolcanic eruption. Triton presents our initial instance of a world where life likely did not emerge early in its planetary history. Our understanding of the early eons of a Kuiper Belt body's existence is limited, which substantiates this perspective. However, contemplate the obstacles confronting the emergence of life on a dwarf planet situated over 30 astronomical units from the Sun. Water and certain organic compounds would be accessible, but energy derived from sunlight and magnetic fields would be minimal. Cataclysmic collisions were likely common, similar to those experienced by larger planets. However, on dwarf planets, cooling occurred more rapidly following the cessation of their equivalent of the Great Bombardment, particularly for those as comparatively diminutive as Triton and Pluto. Although we recognize the potential for rapid life formation, a more cautious viewpoint posits that life on Triton probably emerged subsequent to Neptune's capture rather than prior to it. This is the scenario we suggest for the potential development of life on Triton. Initially, the sole candidate among our 3 proposed habitats for life on Triton would have been the global ocean, rendered liquid by the capture event with Neptune 6. Current models indicate that even with rapid surface freezing, the substantial mass of water and thermal energy would have maintained it in a liquid state for hundreds of millions of years. Access to the surface would have been futile, as sunlight for phototrophy would have been minimal. The UV photodissociation of H2O may have produced some O2 for redox reactions. Nonetheless, chemoautotrophy appears more probable in or adjacent to the ocean floor. As Triton established its initially unconventional orbit around Neptune, it resembled an early Europa. The evolutionary paths for life in the 2 worlds may have closely mirrored each other. This documentary depicts our iteration for Triton, aligning with the steps outlined in the following narrative. Life, based on water and carbon, likely originated with heterotrophic protocells that resided at the bottom and consumed organic compounds from their environment. Microbial chemoautotrophs likely evolved from these ancestral chemoheterotrophs, step 1. They may have been methanogens or microorganisms akin to sulfur ion bacteria. However, we lack the means to ascertain their identity. Thus, we will refer to them in generic terms only. A lithoautotroph likely emerged shortly thereafter, step 2. Life on Triton may have also included a succession of thermotrophs, steps 3 and 4, ionotrophs, steps 5 and 6, or kinetotrophs, steps 7 to 9, as early progeny of the last common ancestor. Detrivores may have also existed, step 10. Hundreds of millions of years were presumably sufficient for complexity to evolve, enabling macroorganisms to filter feed while stationary on the ocean floor, step 11. Drift like jellyfish, step 12. And ultimately adhere to the ice ceiling at the water column's apex, step 13. Given the plethora of food producers, consumers would have inevitably undergone evolution, step 14. The ice ceiling would have also established a new habitat via liquid inclusions within the ice. Pre-adapted lono or osmotrophs ought to have exploited the elevated salinity of these aquatic microhabitats, step 15. The sequestration of psychrophilic chemoautotrophs, step 16, is equally plausible. The evolution of these ice-dwelling organisms would not have signified a drastic shift from their open ocean progenitors. As Triton's orbit progressively became more circular, tidal heating would have decreased. However, sufficient heat persisted, in conjunction with radiogenic heating from the core, to maintain an indeterminate volume of the ocean in a liquid state. The temperature outside would descend to extremes unprecedented in Europa or ultimately any other planet within the solar system. Frigid Titan served as the nearest analogue, and at this juncture in Triton's history, it would have increasingly resembled Titan, and less so Europa. Hydrophobicity would have started to resemble a commendable lifestyle, particularly due to its eclectic combination of organic compounds and their degradation products. How do we transition from hydrophilic organisms to such distinct entities? Should we propose the possibility of life on Triton, we must wholeheartedly accept that life in liquid nitrogen may be essential for survival at temperatures as low as 40 degrees above absolute zero. Silane may serve as more suitable backbones for biomolecules in an oxygen-deficient hydrophobic environment, such as liquid nitrogen. The hypothesis posits that nitrogen-based, silane-derived life forms may have established themselves within the minute cracks, fissures, and inclusions that would inevitably develop in frozen nitrogen. Titan, fittingly, offers a framework for contemplating this issue. Similar to Titan, where the difficulty lay in the transition of life from water-based to ethane-based organisms, such an evolution could have occurred on Triton through two mechanisms. Initially, new life may have originated in the fissures or inclusions within the liquid nitrogen, resulting in a chemoheterotroph capable of surviving in nitrogen-deficient environments. Alternatively, upon the interaction of H2O ice with NZ ice, it is conceivable that transitional forms emerged, gradually evolving from hydrocarbon-based building blocks to silane-based structures. Step 17. Transitional forms initially a combination of H2O and ammonia, NH3, followed by a mixture of NH3 and N2, facilitated the transition from H2O to N2 as a solvent. The feasibility of resolving the issues arising from the disparate melting points of H2O, NH3 and N2 remains ambiguous, as does the potential for biochemistry to occur in these solvents. Despite its apparent improbability, we contend that it warrants consideration. If certain N2-tolerant chemotrophs inhabited liquid nitrogen, fully autonomous forms could have evolved to reside in either inclusions, step 18, fissures, step 19, or both. In liquid nitrogen, biofilm mat-like organisms, proliferating on frozen surfaces, may have led to the emergence of a consumer, step 20. This indicates the existence of a minimum of 2 trophic levels of silane-based life in liquid nitrogen, likely constituting the most peculiar ecosystem within this region of the Oort cloud. Triton and Pluto are inherently dwarf planets and have been assimilated into the category of major planets within our solar system. Pluto remains in the area of its origin, the Kuiper belt of asteroids beyond Neptune. Approximately every 260 years, its orbit approaches the Sun closer than Neptune's for a 20-year period, before retreating with its binary companion, Charon, to a distance of 40 astronomical units from the Sun. Triton is now a permanent resident, having been captured by Neptune from the Kuiper belt to function as its largest satellite. Both bodies exhibit traits typical of asteroids originating from a considerable distance from the Sun. 2/3 to 3/4 of their mass consists of rock, while the remainder is predominantly water. Among the coldest entities ever recorded, the ice is solidified as firmly as stone, at least externally. Alongside methane and its reaction products, including nitriles, it comprises nitrogen, a significant volatile component. Adequate nitrogen envelops the surface, thereby producing a tenuous atmosphere of N2, accompanied by trace quantities of typical gases such as methane, carbon monoxide, and carbon dioxide. Triton is the most peculiar celestial body in the solar system. The surface is both familiar and unique due to the extreme cold-colored chemicals, significant tilt causing seasonal variations between the equator and the poles, and the probable presence of subterranean liquid reservoirs. It is exceedingly rugged and mountainous. Exotic by all terrestrial standards, the prospects for life there seem formidable from our viewpoint, yet not unattainable. The history of Triton's formation and capture indicates that a global ocean enveloped the dwarf planet-turned-satellite following its orbital acquisition by Neptune. Sufficient time should have passed for life to develop, given the presence of organic chemicals and various available energy sources. A trajectory resembling that of Europa is conceivable, albeit likely enveloped in a frozen crust in the near future. Triton is distinguished by its evolution from a Europa-like satellite to one resembling Titan, where organic chemistry is more pronounced. However, Triton surpassed Titan in cooling to the extent that nitrogen solidified. This event has resulted in 3 potential microhabitats: aqueous inclusions within water ice, extensive subsurface pools or possibly an ocean, and reservoirs of liquid nitrogen. If life originated in water on Triton, it probably followed a significant evolutionary lineage akin to that on Europa. The establishment of the liquid nitrogen microhabitat facilitated an unconventional avenue. Nitrogen-tolerant organisms, potentially dependent on silane building blocks, wholly or partially, migrated into the fissures or cavities within the liquid nitrogen. Transitioning from a Europa-like here to there may have posed a challenge. Yet nature exhibits a creativity surpassing human imagination. Our investigation into the potential for life within our solar system strongly suggests that Earth is the sole planet with intelligent species. The only one where at least one species has developed technology, and likely the only celestial body orbiting our Sun that supports organisms of significant size, complexity, and diversity. We will now examine the reasons for the emergence of life with those characteristics on Earth and the implications for the potential existence of complex, intelligent, technologically advanced life in other worlds. The evolution of life on Earth has resulted in a significant microbial biomass, as well as the emergence of large and complex organisms. It has accomplished this by facilitating the proliferation of the microscopic unit of life, the single cell, into integrated colonies that generate substantial living organisms. Moreover, the introduction of cellular differentiation and specialization has produced organisms of significant complexity. They have diversified into numerous forms due to their inherent complexity. Consequently, the Earth's biosphere exhibits significant diversity, encompassing organisms that are both large and small, as well as simple and complex. It is uncertain whether entities of similar size and complexity exist elsewhere in the solar system. There is no evidence indicating their existence. However, we cannot dismiss the possibility until we investigate Mars's lava tube, caves, or Europa's icy crust. They exist in an alternate realm. What justifies our assertion? What justifies the consideration of multicellular, macroscopic life forms on adjacent celestial bodies? Examining certain specific factors that have facilitated the emergence of substantial size, complexity, and diversity on Earth will provide insight into where and under what conditions similar phenomena may occur on other planets. Organisms attain substantial size when the biomass sustaining them is proportionately greater. Biomass is fundamentally determined by the quantity of available energy. Our analysis of biomass pyramids from Chapter 3 indicates that the substantial proliferation of apex consumers is contingent upon a greater biomass of primary consumers and producers, supplying sufficient nutrients and energy to sustain the growth of organisms at the pyramid's apex. Complex food webs and intricate ecosystems similarly rely on a plentiful energy supply. This will assist a substantial and varied array of producers, capable of supplying extensive and diverse groups of consumers. The Earth's virtually limitless solar energy supply, one of the most efficient methods of energizing living systems, facilitates the planet's biodiversity. Earth also contains several macrobiotic constituents of ecosystems reliant on chemoautotrophs that obtain their energy directly from environmental chemicals. These examples serve as analogues for what we hypothesize to be the predominant energy source on planets that may harbor life in dark, subsurface environments. It is significant to note that instances on Earth where organisms attain considerable sizes are confined to deep ocean vents, and the ecosystems they sustain do not extend extensively. All other life forms reliant on chemoautotrophy at the producer level are microbial in scale. A substantial scale derived from any other energy source examined in this book is feasible. However, there is no terrestrial precedent aside from deep ocean vents. The elevated metabolic rates sustaining large integrated organisms are facilitated by interactions between the atmosphere and biosphere. These interactions facilitate the feasibility and self-sustainability of oxidation-reduction cycles. The elevated oxygen levels in Earth's atmosphere facilitate the oxidation of reduced carbon compounds, such as glucose, thereby serving as an efficient method for extracting biologically useful energy. Simultaneously, photosynthesis converts the carbon dioxide generated back into reduced carbon compounds for nourishment and restores the atmospheric oxygen supply. Comparable cycles, not exclusively of oxidation and reduction, although those appear most probable, are essential in any ecosystem aspiring to attain substantial size and complexity. The Cambrian explosion, which resulted in the emergence of the first substantial organisms on Earth, is believed to have occurred mainly due to oxygen attaining a critical concentration in the atmosphere. The mean surface temperature of Earth is approximately 15 degrees Celsius, significantly lower than the temperature at which most proteins denature, around 45 to 50 degrees Celsius, yet considerably higher than the freezing point, 0 degrees Celsius, of water. This indicates that aquatic organisms can thrive in the majority of terrestrial habitats on Earth, specifically where liquid water is present. With the capacity to expand in aerial, terrestrial, and aquatic environments, organisms are not restricted by physical limitations regarding their size. This does not apply to life forms sequestered in soil or encapsulated in ice inclusions, for instance. Seasonal thermal cycles facilitate the evolution of organisms adapted to exploit extreme cold, extreme heat, moderate temperatures throughout the year, and all variations in between. The specialization of bodily structures and organ systems inherently leads to increased complexity. Life is fundamentally confined to temperatures that allow its primary solvent to remain in liquid state. In environments where water serves as the principal solvent, Thermal habitats can encompass the entire spectrum of liquid water temperatures, from freezing to boiling. Multicellular organisms thrive between 0 degrees Celsius and 45 degrees Celsius, and natural selection on Earth has resulted in a diverse array of adaptations across this temperature range. Extremophiles are microorganisms that inhabit the extreme limits of environmental conditions. A diverse array of adaptations results in a diverse array of organisms. Does a restricted thermal range, as observed in solvents other than water, inhibit substantial size and complexity? Not necessarily. However, theoretically, the challenges are more significant. One can envision the development of sizable, benthic organisms in ethane and methane lakes on Titan. The restricted thermal range in such an environment results in fewer degrees of freedom for the evolution of various specializations. The biochemical versatility of non-aqueous solvents is comparatively limited, although this remains uncertain. Numerous organisms exhibit mobility due to the availability of space and suitable temperatures, facilitating dynamic activity. Microorganisms necessitate muscular adaptations and the integration of incoming information with outgoing motor commands. This has resulted in the evolution of nervous systems in terrestrial animals. Intricate nervous systems are correlated with complex, typically larger organisms. The biological utility of mobility encompasses the capacity to pursue prey, evade predators, locate mates, often necessitating a complex behavioral repertoire for mate recognition and copulation, disperse, to optimize resources, and seek refuge. Distinct anatomical and physiological adaptations are necessary to perform each task in diverse manners. Given Earth's characteristics conducive to the development of large, complex and diverse organisms, it is important to acknowledge that life evolved for almost 2 billion years prior to achieving a macroscopic form. It existed as unicellular and prokaryotic for a minimum of 1.5 billion years, representing the most rudimentary cellular organization. Life emerged promptly after its potential was realized, yet it remained uncomplicated and relatively homogeneous for over half of its existence. This indicates that life remains stable and unaltered when it is optimally adapted. The sole instance of life we possess does not provide sufficient data to generalize the speed of life's emergence or the rate of its evolution and diversification under optimal conditions. Our singular sample provides empirical evidence that organisms may necessitate substantial time to attain significant size or complexity, even in optimal conditions. The larger and more intricate the organism, the greater the potential for diversification. Nonetheless, if evolution necessitates substantial time to generate large and intricate organisms initially, the complete evolution of a diverse biosphere demands even greater duration. Once more, we remain uncertain regarding the existence of intrinsic constraints on the rapidity of biosphere diversification. The rate-limiting factor is the velocity of alterations in planetary conditions. Habitats can be categorized according to prevailing or fluctuating temperature, topography, altitude, moisture, sunlight exposure, substrate, rock, soil, sand, or its absence, air, water. Globally, various biomes, including polar, taiga, tundra, alpine, prairie, woodland, desert, and tropical forest, exemplify extensive habitat differentiation. Fractionation occurs from the community to the microhabitat on a highly differentiated planet such as ours. Wherever distinct habitats adjoin or transition into one another, the interfaces or gradients between them create additional habitats. The interfaces on planets such as Earth are extensive, comprising substantial bodies of liquid, water, and substrate, land, in contact at and beneath the surface. The creation of new habitats at the intersections of land and water, land and air, and water and air facilitates enhanced biodiversity. Examine the diversity of organisms in tidal pools at the coastline, along riverbanks, and within the upper layers of a rainforest canopy. In areas with more uniform climate and topography, such as polar regions, biodiversity is significantly diminished. The geophysical history of a planet or moon influences the sequence of organismal evolution, a process that is inexorable. If planetary history has been intricate, the resultant biosphere will reflect its historical fluctuations. During the Mesozoic era, Earth's plentiful energy and temperate conditions facilitated reptiles, particularly dinosaurs, to inhabit and dominate nearly every ecological niche on land, in the air, and in the oceans. Following the catastrophic conclusion of the Mesozoic era and the extinction of the dinosaurs, the remaining heterothermic reptiles were replaced by homeothermic mammals and birds, as global temperatures decreased and vegetation transformed. Consequently, mammals, pre-adapted for homeothermy and internal gestation, along with birds, pre-adapted for homeothermy and flight, emerged as the predominant vertebrates in Earth's biosphere. Even without the event that caused the extinction of the dinosaurs, they could have still prevailed on Earth. Intelligence is defined as the capacity to synthesize experience and predict future outcomes. Upon the evolution of mobile life forms, organisms that procure sustenance through grazing, collecting, or capturing, the nervous systems, or analogous systems facilitating integration and coordination, may attain the requisite complexity for the emergence of intelligence. Intelligence has independently arisen in multiple significant animal groups on Earth, initially manifesting in cephalopods over 400 million years ago. Nonetheless, it has not emerged as a common or prominent outcome of evolution. Technology is the application of energy, tools, materials, and information by a living organism to enhance its influence on the environment. With few exceptions, only Homo sapiens have developed substantial technological capabilities on Earth. We examine the requisite conditions for the development of intelligence and technology, as well as the reasons these conditions may not suffice to produce either outcome. This is due to the infrequency of intelligence and technological advancements. Intelligence is a nuanced phenomenon and notoriously challenging to evaluate from a solely human standpoint. Nevertheless, numerous examples of notable intelligence have emerged throughout Earth's evolution, along with at least one instance of meta-intelligence, figure 12.2. Analyzing these cases elucidates the significant factors that contributed to its emergence. Cephalopods represent the apex of intelligence among all invertebrates. They separated from other mollusks in the late Cambrian period, approximately 500 million years ago. They proliferated and diversified in subsequent eras until experiencing a catastrophic decline during the Permian crisis, 250 million years ago, with only octopuses, squids, cuttlefish, and a nautiloid persisting today. Conversely, those forms are active benthic predators and foragers. They possess highly developed tactile and visual senses, along with intricate motor systems that enable precise movement of their 8 to 10 appendages and complex manipulation of their mouthparts. Cephalopods exhibit a high level of sensorimotor coordination, governed by a substantial brain composed of a complex aggregation of lobes and lobules, with specialized inputs and functions organized hierarchically. The brain identifies 4 tiers of control. 1. Lower motor centers responsible for discrete, unanticipated movements. 2. Higher motor centers facilitating coordinated movements. 3. Memory repositories and receptor analysis, integrating pathways from gustatory, olfactory, and visual sensory receptors. And 4. Lobes implicated in regulating motivation and evaluating rewards. Workers knowledgeable about octopus behavior assert the identification of 11 personality alterations in animals subjected to injury or surgical excision of the subfrontal lobes. Insects diversified to occupy every ecological niche in the coal forests of the Carboniferous period, approximately 300 million years ago. By around 150 million years ago, social insects, such as ants, wasps, and bees, had evolved from their ancestral forms. Biologists do not consider individual social insects to possess intelligence in the traditional sense. However, collectively, they exhibit characteristics that suggest intelligence if regarded as a single entity. They construct intricate habitats, allocate tasks, communicate symbolically, as seen in bees, significantly alter their microenvironment, cultivate food, notably among fungal farming ants, domesticate other species, engage in warfare, and collaborate for the collective benefit. Consequently, they exemplify a form of meta-intelligence. The success of social insects indicates that this type of intelligence is advantageous for adaptation, suggesting that it may be equally important to investigate the extinction of intelligent-like capabilities as it is to study individual intelligence. Parrots and their relatives evolved from flying reptiles during the late Cretaceous period, approximately 70 million years ago. Macaws emerged in the New World, following the formation of the Andes around 28 million years ago, while modern cockatoos appeared approximately 20 million years ago. Parrots, macaws, and cockatoos belong to the order Psittaciformes, recognized for their intelligence, which is often compared to that of certain non-human primates. Their brain-to-body weight ratios can be as high as those of chimpanzees. Most species exhibit strong social behaviors. The African grey parrot is capable of acquiring a vocabulary of several hundred words across various dialects, associating words with meanings and comprehending basic syntax. There is some debate regarding the extent of their cognitive abilities beyond mimicry. However, this mimicry alone indicates significant intellectual capacity. Certain avian species demonstrate the ability for symbolic learning. The sociable Corvidae family, which encompasses crows, jays, and ravens, displays signs of causal reasoning, adaptability, creativity, and planning akin to that of chimpanzees. 5. Whales, dolphins, and porpoises constitute the mammalian order Cetacea. They probably diverged from their terrestrial ancestors near the start of the Cenozoic 65 million years ago, becoming increasingly amphibious, where the buoyancy of the ocean enabled them to become the largest animals on Earth. They also have the largest brains that have ever evolved. The brain of the blue whale measures 9 times the size of the human brain. 6. Saccoceiophones Chiotes. By the Miocene, 20 million years ago, cetacean brains had achieved essentially their modern size. Most of the enlargement of the brain in cetaceans reflects a huge elaboration of the neocortex beyond the sensorimotor primary projection areas. Their extraordinary reliance on hearing and the neural specializations for that sense evolved rapidly once they were totally marine. Other changes in the body have made it possible to make sounds, which has led to a complex echolocation system and a communication system whose full complexity is unknown. Their vocalizations are complex. They are good at learning and imitating distinct vocal signals and appear to be able to recognize and address one another as individuals. 7. They are playful and anticipatory. They are highly social and unquestionably altruistic. Data from field studies have even been interpreted as evidence for cultural transmission in dolphins. Elephants possess the largest brains and neocortical volume among terrestrial animals. Although they are typically regarded as intelligent, their performance on short-term cognitive assessments, including demonstrations of cause-effect learning, is lackluster. They excel in long-term spatio-temporal memory and intricate social interactions. They exhibit self-recognition in mirror tests and display heightened sensitivity to incapacitated and deceased companions. Primates diverged from ancestral insectivores during the early phase of the Great Mammalian Radiation, at the onset of the Cenozoic, approximately 65 million years ago. Simian primates, encompassing monkeys and apes, separated from other primates around 40 million years ago and began to evolve larger brains. By the Middle Miocene, roughly 16 million years ago, apes had become distinct from old-world monkeys, and the common ancestor of chimpanzees and humans diverged from ancestral gorillas. Approximately 6 million years ago, by 4.4 million years ago, humans diverged from chimpanzees and commenced diversification into multiple species. Homo sapiens is the only extant representative of various competing human lineages, attaining contemporary morphology and cranial capacity. Approximately 200,000 years ago, the evolution of hominids demonstrates a continuous progression in. The main characteristic of brain size is the expansion of the neocortex. The anthropoids experienced an evolutionary acceleration in brain size much more recently than the cetaceans, with the human brain surpassing that of the chimpanzee within the last 6 million years, while the neocortical expansion in the cetacea likely exceeded that of humans 20 million years earlier. 10. The acceleration of neural complexity in these two distantly related mammals has thus been a completely independent event. We can see a steady rise in cognitive and behavioral complexity throughout primate evolution. For example, monkeys started social grooming 30 million years ago. Orangutans learned to anticipate 16 million years ago, and gorillas showed signs of being creative 7.5 million years ago. The chimpanzee human ancestor of 7.5 million years ago presumably had the social hierarchies and interactions, capacity for playfulness, altruism, and deceit, and ability to form images and abstract thoughts seen in modern forms 12. Though the capacity for symbolic language must have been present, since modern chimpanzees can master a modest vocabulary and syntax with sign language, a full-blown symbolic verbal language evolved only in humans, probably less than 2 million years ago. Each aforementioned example represents a distinct evolutionary occurrence. The connection among cephalopods, social insects, and vertebrates is so remote that their cerebral structures exhibit minimal similarity. Within vertebrates, mammals separated from the reptilian lineage that would eventually give rise to birds long before significant intelligence developed in either lineage. The last common ancestor of cetaceans and primates likely existed at least 40 million years ago, prior to the acceleration of brain enlargement in either group. Elephants and cetaceans may share a closer relationship than with primates. However, their divergence occurred tens of millions of years before either lineage experienced the selective pressures that resulted in remarkable brain enlargement. Brain enlargement and enhanced cognitive abilities originated from disparate initial conditions in each instance. Another significant observation is the infrequency with which conspicuous intelligence has developed. The groups do not exhibit a unified ecological theme, as they encompass marine, terrestrial, and arboreal flying environments. Are there additional conditions, therefore, that are especially linked to the evolution of intelligence? The following factors seem to have been essential. Size. In all instances of individual intelligence, the animals exhibiting it generally possess larger body sizes than the average for their taxonomic group. Cephalopods, whales, and elephants are particularly significant in this context. It is important to note that this rule does not extend to meta-intelligent forms. Activity level. An active lifestyle necessitates greater sensory processing and motor control compared to a sedentary one. Active organisms navigate a dynamic environment, requiring them to assess aspects that sedentary organisms do not encounter, such as balance, acceleration, depth perception, distinguishing foreground from background, feature extraction, determining if an approaching object is a friend or foe, spatial orientation, and memory for previously experienced locations and situations. Furthermore, such activity demands a system to command and coordinate muscle movements in the appropriate sequence and intensity, necessitating a distinct form of learning. The larger and faster the animal, the more sophisticated and precise its sensory input and motor control must be. These factors drive the evolution of more neural components and their intercommunication. This phenomenon is referred to as cortical neural architecture. The enlargement of cortical brain structures is a prevalent characteristic among intelligent species. The configuration of the cortex facilitates the vertical stacking of nerve cell columns at a high density. An increased number of neurons correlates with enhanced processing capabilities. Another significant aspect of cortical architecture is its topographical mapping of the external environment, whereby information from a specific external location is projected to a corresponding point in the brain. Due to the rapid growth of cortical area relative to brain volume, the cerebral cortex becomes convoluted in mammals. This allows a two-dimensional expanse of brain tissue to represent a greater number of environmental points. In terms of visual imaging, this enhances detail resolution, thereby augmenting the complexity of processed information. Elevated intelligence is consistently linked to intricate sensory processing. Cephalopods and primates analyze visual and tactile stimuli with remarkable precision. Avian species exhibit exceptional acuity in both vision and auditory perception. It is noteworthy that parrots and primates have evolved in visually intricate arboreal habitats. The auditory capabilities of marine mammals rank among the highest in vertebrates, and their echolocation proficiency is likely rivaled only by that of bats. Fine motor control is the counterpart of high sensory resolution. The counterpart of high sensory resolution is fine motor control. Octopuses are challenged by controlling 8 arms, each combining delicate, complex, and complicated mouth movements. Motor control of a complex vocal apparatus facilitates parrots' ability to mimic sounds. Primates likewise have precise control over subtle muscle movements to control vocalization, especially in humans, hand and finger manipulations, and multifaceted facial expressions important in social communication. Detailed coordination of gross limb movements, like those for grasping and throwing objects, has also been an important adaptive advantage for hominids. They evolved from an arboreal lifestyle, which favors the development of grasping forearms and excellent eye-hand coordination, and places a premium on depth perception and acuity. This would have favored integrating visual inputs with other modalities and a corresponding expansion of associative areas of the neocortex. It would also have pre-adapted them for the grooming hallmark of primate social interactions. Social behavior. All vertebrate examples of intelligent animals mentioned are profoundly social. This necessitates advanced communication through behavior, vocalization, or facial expression. It often entails hierarchical and territorial awareness, as well as precise social memory. Consequently, a considerable level of learning, abstraction, high sensory acuity, and refined motor control is essential for suitable social behavior. The hominid example effectively demonstrates the interaction between sensory motor resolution and cognition. A long-held assumption posits that the ancestral apes, which eventually evolved into hominids, transitioned from forest habitats to the newly formed savannas during the early Miocene, over 20 million years ago. Larger body sizes, partial upright posture, enhanced tool use, and the capacity to hunt larger prey on the plains would have intensified the necessity for individuals to possess superior eye-hand coordination, a heightened sense of time, more intricate social structures and behaviors, and improved coordination of group activities. Recent evidence indicates that 2 contemporary human traits, bipedalism and reduced male canine size, were present in Ardipithecus ramidus, which inhabited certain woodlands 4.4 million years ago. This implies that advanced cognition may have been linked to diminished male aggression, food for sex exchanges that fostered monogamy, and the necessity for paternal investment in offspring during early hominid evolution. These social innovations, which are infrequent among mammals, may have contributed to or facilitated the increased encephalization associated with enhanced intelligence. Regardless, humans faced competition from other hominids and each other while navigating the challenges of the Pleistocene ice ages. Concurrently, their neocortex expanded, facilitating language acquisition, improved tool utilization, and cultural development. Trophic level. Typically, organisms at elevated tiers of the food web exhibit greater intelligence compared to their prey at lower tiers. The ratios of brain mass to body mass are generally superior in carnivores relative to herbivores. This may indicate that capturing prey necessitates greater anticipation and behavioral coordination than evading predators. Fear and instinct represent more primitive, ingrained neural functions, whereas planning, anticipation, and learning demand more advanced, adaptable neural circuitry. Most social insects, ants, wasps, and bees, are restricted to the order Hymenoptera, class Insecta, phylum Arthropoda. Socialization has arisen independently in numerous lineages among this group, except for the termites, in no other insect. Order. This has been attributed to the evolution of haplodiploploidy, whereby one sex has one set of chromosomes, haploid, and the other has two sets, diploid. In this case, genetic differences dictate different roles, leading to a caste division of labor, 3. This entails a different repertoire of behavior that appears to be highly rigid and instinctive. While honeybees can communicate precise information about direction and distance, their communication system is highly stylized and apparently literal. Thus, the behavior of individuals shows no evidence of the plasticity normally associated with intelligent behavior. Still, the aggregate effect of many individuals serving different roles results in outcomes that appear quite intelligent if conducted by a single individual. This case of meta-intelligence has astrobiological significance, because it could be a different way for life to arrive at intelligent ends on another world without the necessity of evolving individual intelligence as we recognize it on Earth. It appears intuitively evident that intelligence confers a selective advantage, suggesting it should be a preferred evolutionary outcome. If this were indeed the case, intelligence would be more prevalent than it currently is. Undoubtedly, life on Earth has demonstrated a consistent advancement in the evolution of increasingly intelligent organisms. Swordfish surpass jellyfish in intelligence. Reptiles exhibit greater behavioral plasticity than amphibians. And primates are more intelligent than any representatives of the insectivores from which they evolved. Nevertheless, only a limited number of species within a specific lineage display a qualitative enhancement of intelligence among most animals. Plants and microbes, which constitute the majority of Earth's biomass, entirely lack intelligence. Consequently, our intuitive premise must be erroneous. Intelligence is an emergent characteristic of biological attributes, including brain mass, neural architecture, and circuitry. The expansion of the neocortex facilitates intelligence. However, the initial expansion occurred to accommodate the integration of high-resolution sensory information and the coordination of precise motor activities rather than to enhance cognitive capacity. Once the foundational elements for intelligence were established, natural selection could subsequently favor them for their intrinsic value. Examine the scenario involving two mammals, the gazelle and the lion. Evolution has favored the emergence of a substantial brain with an enlarged forebrain for the processing of intricate sensory information and advanced motor control in both species. Nevertheless, the results diverge between prey and predator. The gazelle exhibits exceptional sensitivity and agility, but possesses lower intelligence, whereas the lion, though less nimble, demonstrates greater cognitive capabilities as it pursues its prey. The inquiry arises as to why intelligence developed in lions but not in gazelles. A partial explanation is that gazelles prioritize speed over intelligence for survival. Their ability to evade predators 11 out of 12 times substantiates this approach. However, their success diminishes when multiple lions collaborate in hunting, a behavior necessitating enhanced coordination and intelligence. Natural selection perpetually equilibrates, distinct strategies, one for evasion and another for predation, in the evolution of both prey and predator. From a foundation of varying advantages, selection favors the gazelle's speed over intelligence and the lion's intelligence over speed. This evolutionary outcome illustrates that both swiftness and intelligence confer significant advantages. Is there more to this issue? Is intelligence maladaptive in certain contexts? Neuroscientists lack sufficient understanding of intelligence and its underlying factors to provide a definitive answer. The neural modifications necessary for effective information processing, integration, and learning may detract from other essential capacities. Additionally, intelligence might result in counterproductive social and behavioral intricacies. Simpler behaviors and less complex social structures often enhance group survival. This could elucidate why intelligence seems underutilized in certain instances. Lastly, intelligence may be self-limiting, a notion that becomes more apparent when considering the implications of technology, which requires creativity as a prerequisite. The genesis and destiny of technology possess evident astrobiological significance for two primary reasons. Firstly, any comprehensive data we may acquire regarding extraterrestrial life, as well as any insights that such life may obtain about us, will necessitate advanced technology for detection, analysis, and eventual exploration of other worlds. Secondly, technology surpasses biological constraints, and consequently could significantly influence the trajectory of its biological antecedents and/or their successors. The human species on Earth has significantly advanced technology. Given that this is the only known instance in the universe, formulating a general hypothesis regarding the origins of technology is at best problematic. We are unable to account for essential factors when analyzing our specific technological development. Approximately 200,000 years ago, humans underwent a swift expansion of the forebrain, facilitating the precise motor control necessary for tool utilization and vocalization, while also augmenting cerebral regions associated with planning and abstract reasoning. These advancements culminated in the emergence of symbolic spoken language, enhancing interpersonal interactions in increasingly intricate manners, thereby fostering the establishment of rudimentary hunter-gatherer societies. The initial departure from complete subservience to environmental conditions was the discovery of how to initiate and control fire. This innovation afforded humans a concentrated and manageable energy source, offering warmth, enhancing their diet through cooking, and safeguarding them from predators. Subsequently, it would evolve into a crucial tool for fabrication. The subsequent pivotal advancement in technology was likely the domestication of wild animals, particularly dogs and various ungulates. Throughout the protracted period required to develop language, enhance tools, and master the initiation and regulation of fire, humans sustained themselves through hunting and gathering. In the process, they gained extensive knowledge about flora and fauna, ultimately achieving the capability to cultivate and breed animals, thus ushering in agriculture. With the establishment of agriculture as a fundamental aspect of human culture, an individual could produce more food than necessary for their own sustenance. This surplus facilitated the division of labor and ultimately resulted in social stratification, complex cultural frameworks, and highly organized social interactions, collectively known as civilization. The advent of civilization facilitated the construction of edifices and armaments, reliant on the smelting of ores to produce metallic artifacts. This expertise augmented the more primitive crafts of pottery, papermaking, textile production, and other items derived from natural resources. By employing manufactured objects and domesticated fauna, humans began to manipulate and influence their surroundings to a degree unparalleled by any other species. Thus, technology emerged. Mathematics catalyzed technological progress. Initially influencing agriculture, it subsequently transformed travel and navigation, evolving ancient astrology into astronomy, and necessitating an understanding of geometry and various computational methods. As the practicality of mathematics became apparent, its application proliferated across nearly all human activities involving physical manipulation. Machines were engineered with mathematical accuracy. Science expanded comprehension of the natural world, and new energy sources were harnessed, empowering humanity to manipulate their environments increasingly. Ultimately, machines were developed for computation, and computers advanced information processing to a speed that rivaled, though not yet matched in complexity, the human brain. Presently, the convergence of computers and machines has led to the emergence of robotics, initiating a trajectory toward the creation of mechanized entities possessing some fundamental characteristics of living organisms. Neural complexity, the foundation of intelligence, constitutes merely one of several prerequisites for technological advancement. The creation and manipulation of technological instruments necessitate the capacity to contemplate alternatives, envision non-existent structures and functions, predict outcomes, and ascertain quantitative relationships. Nevertheless, a minimum of 3 additional factors must emerge for technology to develop. Material complexity necessitates the availability of resources for construction and fabrication. In human contexts, this included stone, wood, and animal byproducts such as fur, gut, and bones. Ultimately, the extraction and smelting of metal ores became crucial. Controllable energy. The mastery of fire was pivotal in humanity's advancement in technology. Beyond its function in safeguarding and offering partial autonomy from environmental factors, it was vital for metal smelting. Subsequently, other forms of controllable energy, such as machinery for harnessing wind and water power, and eventually electricity, supplied the concentrated energy required for manufacturing. Manual dexterity is essential. On a planet such as Earth, where materials and energy are plentiful, an intelligent entity must possess the ability to manipulate these resources with precision. This necessitates fine manual dexterity, which is facilitated by appendages equipped with individually controllable digits, such as fingers. An examination of the few instances of conspicuous intelligence evolution elucidates the rarity of technological advancement. 2 of our examples pertain to marine organisms. Cetaceans, whales, dolphins, exhibit high intelligence, exceptional sensory capabilities, and intricate communicative skills, yet they lack manual dexterity. Cephalopods, octopuses and squids, possess sophisticated nervous systems and manual dexterity. However, even if cephalopods were sufficiently intelligent for abstract reasoning, and cetaceans possessed some ability for object manipulation, it remains dubious whether the requisite material resources for tool and machine fabrication could be procured from the relatively uniform marine environment. Additionally, the acquisition of controllable, concentrated energy presents another challenge. Fire cannot be utilized underwater. While hydrothermal vents provide concentrated thermal energy, they are neither portable nor controllable. Consequently, despite 4 billion years of evolution, the marine environment continues to present obstacles to technological advancement. The terrestrial environment offers material complexity. However, among highly intelligent animals, only primates possess the manual dexterity required for precise manipulation of objects and materials. Parrots exhibit fine, manipulative skills with their beaks, and elephants demonstrate considerable dexterity with their trunks. Nonetheless, neither species can execute the micromanipulation necessary for threading a needle. The limb structure of primates, which facilitates the throwing of objects such as stones or spears, may also constitute a crucial form of object manipulation, signifying a substantial competitive advantage. The example of meta-intelligence is compelling, as social insects construct moderately complex structures, such as honeycombs and intricate termite mounds. Although these insects are individually smaller than those exhibiting individual intelligence, they suggest the potential of collective meta-intelligence. The absence of advanced, adaptable technology among these meta-intelligent organisms may indicate that intelligence has not been essential for evolutionary success in numerous lineages. If other conditions are met, it would be premature to conclude that meta-intelligent life forms are incapable of developing technology. In the summer of 1950, Enrico Fermi, the eminent nuclear physicist, was having coffee with his colleagues at Los Alamos, New Mexico, when he abruptly inquired, "Where are they?" When prompted to clarify, he reiterated the inquiry. If technologically advanced extraterrestrials exist, why have they not visited Earth? Or if they have, why is there no awareness of their presence? Consequently, the paradox associated with Fermi posits that, based on statistical reasoning, aliens with sufficiently advanced technology should exist. Yet there is no evidence to support this. If they indeed exist, would they not possess the means to be aware of life on Earth and reveal themselves to us by now? Numerous explanations for the Fermi paradox have been suggested. Notably, Stephen Webb proposed solutions, none of which were sufficiently compelling to prevent him from concluding that extraterrestrial civilizations likely do not exist. This level of pessimism is unjustified. However, I concur that the paradox is genuine. While we are not ready to provide a conclusive solution, we wish to present the following observations. Statistical evidence suggests that the likelihood of encountering extraterrestrial intelligent life, ET, is relatively low. This reasoning is founded on the premise that the probability of contact is the multiplication of several factors, each possessing a low probability. These factors include remoteness. Concurrently, existing extraterrestrial intelligences, ETIs, are likely to be widely dispersed. Approximately 130 stars reside within 20 light-years of our solar system. Unless the probability exceeds 1/130th that one of these stars hosts planetary bodies with an ETI, the nearest ETI, based on statistical analysis, is at least 20 light-years distant. If stars maintain this density from our Sun in a flat plane extending to 100 light-years, the probability must surpass 1/32,500 to anticipate an ETI within that range. Although these odds appear relatively favorable for the existence of another ETI, 100 light-years remains a considerable distance. If an extraterrestrial intelligence, ETI, was situated 100 light-years from Earth, its antennas could perceive the inaugural human-generated radio signals, which are merely a century old. Given that our nearest ETI neighbor could exist in any direction, the probability of inadvertently detecting our electronic emissions or encountering us during a mission for an alternative objective is consequently diminished. Furthermore, considering that Earth is not an especially prominent planet, the likelihood of an accidental discovery remains minimal even within our own solar system. Earth represents a diminutive target within an expansive cosmos. We are operating within a limited time window. If an ETI on another world is relying, as our own search for extraterrestrial intelligence, SETI project does, on radio transmissions of obvious technological origin, they are just now entering the time window within which they can detect us, unless they are closer than 100 light-years away. But they have known about us by some means or another long enough to beam an electronic signal directly at us. We have only been able to detect such signals ourselves for about 100 years. What if they decided to show up and could do so? They could plop down in the middle of the Rift Valley of Kenya in spaceships lit by flashing neon lights. And no living being would know what to make of them unless they timed their landing within the past 2 or 3 million years. When humans smart enough, maybe, to distinguish them from flying birds, would have been present. If they chose to land in central Kansas, they would have had to do so within the last 10,000 years to gain recognition. Considering that life has existed on Earth for at least 3.5 billion years, and may have existed much longer on the planet from which the ETI mission was launched, hitting precisely within the time window of 2 million years or 10,000 years, 0.06% and 0.0003% of life's existence, respectively, would be highly improbable. Communicability. Should an extraterrestrial intelligence inadvertently discover Earth's physical presence or detect intriguing electronic signals from our distant region of the universe, these alien observers must possess the capacity to interpret the information and identify it as originating from a form of life. The detection of technological information from space necessitates a comprehensible language. The plaques and recordings dispatched into space with our spacecraft represent generic methods of conveying information that are intelligible to our cognition, but may not resonate with an alternative intelligence. An extraterrestrial intelligence, ETI, may have opted against visiting us for several reasons, despite its awareness of our existence. If its technology surpasses ours, it may regard us with as little interest as we do ant colonies. Historical precedents suggest that interactions between intelligent entities of disparate origins often culminate unfavorably for the technologically inferior species, as evidenced by human history on Earth. Furthermore, if our potential visitors share a similar organic chemistry, they may recognize the peril of infectious diseases for both parties. Humans exhibit no reluctance in reaching out to extraterrestrial beings. Our inherent curiosity has generally benefited us. Combined with our advanced cognitive abilities, it has allowed us to swiftly assimilate knowledge about our environment and adjust accordingly. Nevertheless, this curiosity may be imprudent and potentially perilous in this context. Any extraterrestrial intelligence capable of contacting us in the near future will possess significantly superior technology. At best, we will lack control over the circumstances. If our prospective visitors are benevolently inclined, they understand that maintaining our ignorance of their existence is optimal. We generally propose one of two interpretations of this stance. The first asserts that extraterrestrial beings have visited us in the past and continue to do so intermittently, yet they maintain a distance, refraining from contact for various aforementioned reasons. A variation of this interpretation posits that extraterrestrial intelligences have indeed established contact through diverse means, including human abductions, animal mutilations, and other anomalous occurrences. The second interpretation suggests that extraterrestrial entities are, in reality, coexisting with us, camouflaged as ordinary humans or other life forms. A continuous influx of reports regarding unidentified flying objects, UFOs, and historical occurrences associated with them purportedly bolsters the notion that extraterrestrial beings have visited Earth in the past and continue to do so. The overwhelming majority of UFOs can be conventionally explained upon thorough investigation. Moreover, no tangible evidence of UFO spacecraft or remnants of exotic life forms has been presented, a fact widely acknowledged by a scientific community eager to validate such findings. Consequently, while the concept of UFOs as genuine alien spacecraft, either dispatched by or transporting extraterrestrial intelligence, garners considerable enthusiasm, it must remain a theory until objective evidence is provided that achieves substantial scientific consensus. The characteristics attributed to UFOs resemble those of advanced spacecraft. They exhibit unusual or unidentifiable forms, possess the ability to hover effortlessly, and accelerate at physically implausible velocities, with or without auditory emissions. This renders us less inclined to entirely dismiss the notion of extraterrestrial visitation. The alternative interpretation of the concept of extraterrestrial visitation posits that aliens coexist among us, indistinguishable from other life forms, including humans. Men in Black examines this premise through artistic expression and humor. Despite the challenge of discerning the intentions of these extraterrestrial entities, unless they share our irrational curiosity, no biological or mechanical artifacts indicative of their presence have been discovered. Although proponents of this theory exhibit fervent enthusiasm, there is no substantiating evidence to suggest that aliens, possessing superior intelligence and technology, would prefer to assimilate into humanity rather than annihilate or exploit us. Although purely speculative, it is plausible that technology is intrinsically self-limiting and incapable of sustaining exploration. Any extraterrestrial intelligence that advances to a technological stage likely leads to its own rapid demise. This may occur due to rendering its home planet uninhabitable before survivors can colonize another world, or because the technological capacity for competition and destruction outpaces the ability of natural selection or programmed evolution to mitigate such destructive tendencies. The counter-argument posits that, even if this is true in most instances, exceptions must exist somewhere in the vast universe. While this is a reasonable assertion, it does not address the improbabilities outlined in section 12.4.1. Indeed, if technology is predominantly self-limiting, this constrains the time frame within which a cognizant and technologically adept life form can establish contact with extraterrestrial entities. Argument by analogy. The discovery and fate of the Hawaiian Islands. A volcanic hotspot in the Pacific Ocean generated the principal Hawaiian Islands between 0.5 and 5 million years ago. The most recent, the Big Island of Hawaii, emerged approximately 500,000 years ago. Life gradually established itself on the island through immigrant species, and evolved in isolation along a distinctive path. Humans first arrived, likely between 300 and 500 BCE, introducing a species capable of creating a Stone Age culture that has endured to the present day. Long before the arrival of humans in Hawaii, civilization had proliferated across much of the globe, achieving a technological and social sophistication in the Eastern Hemisphere that significantly surpassed that of the Hawaiian Islanders. It was not until 1778 that any individual from the advanced nations of the East established contact with the inhabitants of Hawaii. As of 1777, the Hawaiians believed theirs was the sole manifestation of intelligence in the world. Hawaii's isolation and diminutive size delayed its discovery by a technologically advanced civilization, until 2,000 years after human settlement and 500,000 years post-emergence from the ocean. By the advent of a Stone Age culture in Hawaii, the East had progressed to the Iron Age. Nevertheless, 2,000 years would pass before contact occurred, which transpired 300 years subsequent to the development of open ocean navigation in the Eastern Hemisphere. The initial interactions between Hawaiians and Europeans were favorable but short-lived. Conflict soon emerged, compounded by existing inter-island warfare among the natives, while European diseases ravaged the indigenous population. Within a century, settlers from Europe, Asia, and North America effectively seized control of the islands from the native inhabitants, instituting a foreign culture and technology. For 2 millennia, the remoteness of the Hawaiians protected them from technologically advanced aggressors, as they could not publicize their existence across the expansive Pacific Ocean. Once discovered, they swiftly succumbed. The history of life on Earth indicates that specific factors promote a net augmentation in the size and complexity of individual organisms over time. These factors encompass a plentiful energy supply, temperatures conducive to life on the surface, in the atmosphere, and in substantial liquid volumes, a mobile lifestyle, and sufficient evolutionary time. Furthermore, biodiversity is more probable in environments characterized by widely dispersed habitats, frequent seasonal and global temperature fluctuations, extensive evolutionary periods, and a complex planetary history. Intelligence has independently evolved multiple times on Earth. Yet conspicuous intelligence has emerged infrequently, with cephalopods, marine mammals, select avians, elephants and primates as the primary exemplars. Although social insects lack individual intelligence, they exhibit remarkable meta-intelligence in collective behavior. Factors such as substantial size, an active lifestyle, pre-adapted anatomical structures of nematodes, elevated sensory resolution, refined motor control, and intricate social interactions appear to have facilitated the evolution of intelligence. Intelligence is essential yet insufficient for technological advancement. In addition to cognitive ability, an intelligent entity must possess manual dexterity, access to concentrated and controllable energy sources, and suitable material resources. Even if intelligent technological civilizations are inclined to explore beyond their home planets, the likelihood of encountering another such civilization is diminished by the vastness of space and the extensive duration of time that separates them. Consequently, the inability of humans to communicate with or be contacted by an extraterrestrial intelligence is neither unexpected nor indicative of their non-existence. Our material universe is approximately 1.37 billion years old, and the solar system has existed for approximately 1/3 of that duration. The likelihood that life has developed longer than in other areas of the cosmos is evident. However, has it remained, and is it still present? This bifurcated inquiry necessitates a bifurcated response in any particular case or context. Initially, we aim to ascertain whether and under which conditions life may have originated and developed. Secondly, we must inquire about the conditions and duration of its potential existence. The preceding documentaries have predominantly concentrated on the initial issue. We now focus on the second aspect, not only due to its intriguing nature, but also because it has practical ramifications for our anticipated longevity and the circumstances surrounding our eventual demise. The theory posits that all life forms will diverge in one of three directions once they have sufficiently evolved from their ancestors to be deemed distinct. 1. The historical record of life on Earth substantiates this notion. Initially, novel forms typically emerge rapidly, in geological terms, acquire optimal adaptations for their respective environments, and subsequently reach an evolutionary plateau, where form and function remain relatively constant for extended periods due to stabilizing selection. Ultimately, most species inevitably face extinction as the biotic or abiotic environment evolves more rapidly than the organisms can adapt. Third, and infrequently, a lineage may attain a highly advantageous adaptation, resulting in a significant transformation to an entirely new array of descendants that proliferate into the novel opportunities presented by evolutionary innovation or environmental alteration. Most life at any moment exists in a plateau phase of evolution. This occurs because stabilizing selection prevails over directional selection, prioritizing the maintenance of organisms' current traits rather than altering them, provided the environment remains stable. Significant Earth surface alterations, such as climatic shifts and landform modifications, typically occur gradually. Ecosystems generally achieve a stable equilibrium or predictable cycles unless disrupted. In the short term, the physical and biological characteristics of the environment remain relatively stable for species, yet they fluctuate for individuals. This indicates that any mutations or evolutionary processes that alter organisms' adaptations to their environment are selected. Prolonged alterations in environments and ecosystems necessitate that organisms adapt or confront extinction. Nevertheless, numerous instances exist of lives that remain largely unaltered over extended durations. The microbes represent the most notable example. The archaea and eubacteria, the two primordial life forms on Earth, retain the same uncomplicated unicellular structure as their progenitors. Bacteria continuously evolve to circumvent novel pharmaceuticals or mutated threats. Yet fundamentally, they retain slight differences from their form at least 3.5 billion years ago. Parasitic forms are especially susceptible to the plateau scenario, as they inhabit relatively stable environments despite the evolution of their hosts. Diplomonads, such as Giardia, are parasitic cells characterized by two nuclei that infect the digestive systems of vertebrates and induce diarrhea. They have undergone minimal change since they evolved from prokaryotes to primitive eukaryotes. Cyanobacterial progeny of the initial photosynthetic organisms have preserved their rudimentary bacterial structure and function for more than 2 billion years. In the plant kingdom, bryophytes, mosses, which are among the earliest terrestrial organisms, continue to cover the floors of our cool, damp forests after 360 million years. Flatworms such as planaria, arthropods like the horse's shoe crab, and mollusks like the nautilus are distinguished by their remarkable success and stable morphology among invertebrates. Sharks have not fundamentally altered their morphology, physiology, or lifestyle among vertebrates since their emergence 400 million years ago. The effective defensive morphology of turtles has persisted unchanged for 200 million years. Notwithstanding the persuasive instances of biological resilience outlined above, most organism groups ultimately confront extinction. Optimal adaptations are fundamentally irreversible. Consequently, adjustments cannot be implemented swiftly enough when environmental changes or disasters occur. Extinctions transpire continuously, with one species disappearing at a time. Many biologists assert that Earth is experiencing a substantial extinction event, with more species perishing than are produced through evolution. To illustrate our argument more vividly, we need only reference several of the more prominent and remarkable extinctions in Earth's biological history. In the early stages of animal evolution, a group of organisms known as the Ediacaran fauna experimented with various body forms. During the Cambrian explosion 540 million years ago, the experimental forms were supplanted by more competitive and stable body types, including arthropods, bivalve mollusks, and ultimately vertebrates, which would dominate the animal kingdom. In the Devonian period, placoderms, armored fish, dominated the oceans. But by the conclusion of that era, their more nimble, unarmored progeny supplanted them. Two significant extinction events transpired 251 million and 65 million years ago. The initial event, likely resulting from a natural catastrophe during the transition between the Paleozoic and Mesozoic eras, eradicated more than 80% of all animal species. The second event, believed to have resulted from the collision of a massive meteor at the Cretaceous-Tertiary boundary, precipitated the swift extinction of dinosaurs and numerous other significant terrestrial and marine taxa. Transformative innovation occasionally emerges from the seeds of disaster and adversity. The small, predominantly nocturnal mammals were excluded from daytime habitats for the 150 million years, during which dinosaurs dominated the Earth, thus necessitating the development of homeothermy, the capacity to sustain a high, stable internal temperature, to remain sufficiently active for foraging in the safety of night. Following the extinction of the dinosaurs, this innovation facilitated the subsequent significant evolutionary diversification. The existence of air bladders in fish, which enhance buoyancy in water, constituted a pre-adaptation that evolved into lungs when lungfish began migrating through the air between desiccated pools. The development of lungs provided amphibians and their descendants with a novel mode of existence, as they gained access to significantly higher oxygen levels in the air than water. Other innovations have emerged more gradually, yet have equally significant consequences. Jawless, filter-feeding fish evolved into formidable predators, as their anterior gill arches progressively enlarged and became more articulated. This necessitated alterations in their nervous systems and musculature to regulate and synchronize a larger physique and a more dynamic lifestyle. The development of feathers, likely initially for thermoregulation, and alterations in limb morphology transformed arms into wings, allowing birds' reptilian ancestors to achieve flight. In each instance, jawed fish, air-breathing organisms, and flying reptiles, transitioning to a novel mode of existence, resulted in a significant diversification of progeny into new ecological niches and unexploited lifestyles. Our capacity to conjecture about the magnitude of biodiversity in our solar system and beyond is significantly constrained by our insufficient understanding of life's adaptability. Specifically, the degree to which it can flourish in environments dissimilar to those on Earth. The potential for life to be founded on elements other than carbon, utilizing solvents apart from water, and deriving energy from sources beyond light and chemical reactions, is significantly consequential. We observed the beneficial characteristics of carbon-based, aquatic, light-driven, and some chemically supported organisms. The diversity and intricacy of Earth's biosphere align with theoretical predictions. It is possible that life cannot exist in any alternative manner. This is the familiar scenario, as it presupposes a biochemical foundation for life akin to our current understanding. This scenario will evidently restrict the existence of life to those environments where carbon-based polymers, liquid water, and suitable levels of light and chemical energy are present. We have consistently maintained that alternative building blocks, solvents, and energy sources may sustain forms of life unknown to us. This scenario will be referred to as the exotic scenario, as it involves life forms with biochemistry entirely alien to our experience. It broadens the range of environments in which life could emerge and endure. Biodiversity in the solar system within the conventional framework. If one posits that life can solely thrive in aqueous environments composed of carbon-based polymers, then it should have emerged early in the developmental epochs of Venus, Earth, Mars, Europa, and potentially some of the larger icy moons such as Ganymede, Enceladus, Titania, and Triton. Consequently, life would have been extinguished if a habitat became excessively cold to maintain water in its liquid state. Life on Venus can only be sustained by microbial sulfuric acid droplets in the clouds. Earth currently fulfills all prerequisites for the emergence of large, complex organisms and the sustenance of an extensive microbial biosphere, including conditions conducive to the evolution of intelligence and technology. The remaining planets, which can still support certain biospheres under the known conditions, necessitate sequestration below the surface. This refers to the soil or caverns on Mars, where mobility would be significantly restricted. The lack of substantial energy sources will likely confine any remaining life on Mars to small, largely immobile, and predominantly microbial forms. Life may exist in the known conditions on Europa, and potentially 2 or 3 larger icy satellites, but solely beneath the surface ice layer. Provided that energy is sufficiently abundant to sustain the ecosystems that foster such organisms, substantial quantities of liquid water would not prevent organisms from evolving into large, complex forms. Considering the most peculiar scenarios for life in solvents other than water, extremely frigid moons such as Titan and Triton may harbor living organisms, even in the present era. The chemical constituents on Titan are expected to be carbon-based due to the prevalence of organic compounds. Silane polymers on Triton may generate intricate chemical building blocks in liquid nitrogen. In both scenarios, all life forms must exist beneath the surface. Speculating on the size and complexity of potential organisms that may have evolved beneath Titan and Triton is challenging without knowledge of the volume of their liquid reservoirs and their biochemistry. Due to the extreme cold, significant mobility is improbable for any life form. Consequently, intelligence development, even in an unconventional context, appears improbable, rendering Earth the sole planet in the solar system anticipated, based on theoretical considerations, to support intelligent life forms. When extrapolating the potential for life in our solar system to other celestial bodies beyond our vicinity, we are additionally constrained by insufficient knowledge regarding the typicality of our solar system compared to others. This may not be as grave as it seems, however. Our solar system contains various instances of what will likely be discovered elsewhere. We possess terrestrial planets in proximity to the Sun, gas giants in more distant orbits, greenhouse environments, frigid deserts, airless celestial bodies, tumultuous volcanic moons, diverse atmospheric compositions, hydrocarbon plains, and petrolakes, as well as captured satellites in inappropriate orbits. The sole category of the world absent from our sample is the gas giant orbiting near its central star. These are known to exist as they comprise the majority of exoplanets identified to date. Although no similar planet exists in our vicinity, we can infer its characteristics and assess the likelihood of it being capable of supporting life by employing the principles outlined in this book. The habitable zone is often regarded as the range of distances from a central star where planets may sustain life, as these are the regions where water can exist in liquid form. The implicit presumption is that water must exist in a liquid state on the surface. The habitable zone may delineate the spectrum in which Earth-like planets exist or have existed. Our solar system demonstrates that water can exist as a liquid or liquid solution beneath the surfaces of celestial bodies, extending to their outer boundaries, contingent upon the presence of internal energy sources. Consequently, we deem the habitable zone to possess minimal utility. In the preceding film, we contended that intricate ecosystems conducive to the emergence of substantial and complex life forms are more probable in environments characterized by highly fragmented habitats, such as those where life can flourish on the surface. In that regard, a habitable zone, potentially rebranded as a zone of macrobiotic complexity, would be justifiable. Our solar system generally contains numerous planets and moons where liquid water can exist, albeit only under conditions that preclude the emergence of large and complex organisms. Suitable conditions and historical context for advancing intelligence and technology are exceedingly rare. If these assumptions are valid, water-based life may be relatively prevalent, whereas large, complex organisms would be less common, and intelligent life would be scarce. In the context of exotic scenarios, the habitable zone concept is rendered even less useful, as it would vary with each unique combination of conditions, contingent upon the characteristics of the life forms involved. Within our solar system, every planet and the majority of their significant satellites, potentially excluding Mercury and our Moon, could satisfy the criteria for either the carbon-based, water-dependent life forms we recognize, or unconventional life forms yet to be discovered. Given the assumption above, we must conclude that life in the universe is relatively ubiquitous under the exotic scenario. We do not imply that every solar system must possess some form of life. Even in exotic scenarios, planetary history and other factors may frequently inhibit the origin and persistence of life. The universe's enormity must encompass many worlds that support life. Although rare in percentage terms among worlds capable of supporting life, the absolute number of such worlds is likely substantial. The more challenging aspect to estimate is the ratio of worlds where life would be considered exotic rather than familiar from our perspective. If our solar system is representative, more than half of the planets either possess or may have possessed liquid water, suggesting that life or its remnants would be recognizable to us. Nevertheless, we cannot validate the hypothesis that our solar system is representative. Given the rarity of worlds where water can serve as a solvent and the absence of such exotic scenarios, our assumption of the ubiquity of life in the universe must be moderated. This commences by juxtaposing two models of life on any planet. The initial model was the rare Earth model, articulated most clearly and effectively in the eponymous book by Peter Ward and David Brownlee, 3. This model posits that complex macroorganisms evolve infrequently due to the conditions required for carbon-based, water-dependent life to thrive on a planet like Earth, which rarely align simultaneously. As a result, Earth-like planets are uncommon, as is the type of life that has developed on Earth. The rare Earth model necessitates what we refer to as the familiar scenario. Ward and Brownlee advocated for the rare Earth model, but conceded that microbial sequestered life may be significantly more prevalent. We have established this as an alternative yet compatible model termed life unseen. The rare Earth and life unseen models collectively represent the essence of life across the universe. Notwithstanding this refinement of possibilities, even within the limitations of the rare Earth hypothesis, it is almost unimaginable that the evolution of distinctly intelligent, technologically sophisticated life forms has not transpired elsewhere in the universe. Conversely, this occurrence has likely transpired numerous times in various locations. Life on Earth will eventually cease as the planet is engulfed by the dying remnants of an expanded sun in the concluding stages of its natural life cycle. Like all stars of comparable mass to our Sun, hydrogen fusion into helium at its core progressively elevates the star's density mass per volume, resulting in a more intense luminosity. The Sun's energy output escalates by approximately 10% every billion years. This indicates that planetary bodies and their satellites endure extreme heat and radiation as they gradually move away from the Sun. In approximately 5 billion years, the Sun will deplete the hydrogen fuel in its core. The core will succumb to gravitational forces, reaching temperatures sufficient to facilitate helium fusion into carbon and oxygen. Simultaneously, its atmosphere destabilizes and expands, converting the Sun into a colossal red giant star. As the helium supply depletes, an inert accumulation of carbon and oxygen forms at the core. The star subsequently expels its outer layers in concentric shells, resulting in a core that becomes a remnant white dwarf, a dense, hot star comparable in size to Earth, comprised of carbon and oxygen, which has depleted its fusion fuel sources. Subsequently, the Sun will progressively diminish, becoming increasingly dim until its illumination is ultimately extinguished. As the red giant Sun expands to over 100 times its original size, it will engulf Mercury, Venus, and possibly Earth. Earth will become uninhabitable in approximately 5 billion years as it progresses along a trajectory similar to Venus, leading to a runaway greenhouse effect. How can we anticipate alterations in the biosphere before that occurrence? There is no basis to presume that the generalized outcomes of plateau, extinction, and transition, outlined in section 13.1, will not persist as long as Earth's conditions remain conducive to life. Mammals, reptiles, and amphibians are experiencing a significant decline in biodiversity, whereas birds appear to be increasing in number. Invertebrates, particularly insects, dominate the biodiversity spectrum, whereas soil-dwelling roundworms retain a significant yet inconspicuous advantage in biomass among organisms above the microbial tier. As the climate undergoes gradual changes, certain species will become extinct, while a limited number of new species will arise. However, the predominant groups of organisms are likely to endure. Plants are highly responsive to temperature, moisture, nutrients, and animal dispersal agents. Consequently, they will alter or remain constant about fluctuations in local climate, fauna, and their parasites. At this juncture in Earth's biological history, technological human intervention is commencing to exert a significant influence. Genetically modified plants will progressively influence plant communities, and domesticated animals may undergo analogous effects. Genetic modification, including the direct addition or removal of genes and selective breeding, is expected to alter domesticated animal populations to human preferences. These hereditary alterations can occur swiftly, enhancing the survival of animals favored by humans beyond the threshold where natural selection may have resulted in their extinction. Technology and human intention will influence the evolutionary path of specific organisms. This directed selection will subsequently integrate with Darwinian evolution through natural selection, as a significant factor influencing the destiny of any species. In certain species, such as humans and domesticated flora and fauna, Intentional selection will predominate their evolution. Changes in a specific species may influence other species through a cascading effect. Thus, directed selection could indirectly impact a significantly larger segment of the biosphere. Moreover, advancements in robotics will further alter the trajectory of mechanical evolution, leading to increasingly sophisticated lifelike machines that may threaten or supplant living organisms, including humans. Individuals will increasingly find it simpler to alter significant aspects of the climate, intentionally or otherwise. 4. This indicates that humans will exert a greater influence on the biosphere. The future and destiny of humanity necessitate an examination of the concurrent evolution of humans and machines. Biomedical technology has progressed to a stage where synthetic components, including prosthetic limbs, pacemakers, and hearing aids, can enhance the human body. Advanced computerized mechanical devices facilitate communication for stroke victims, mobility for the paralyzed, and vision for the blind. Since the inception of tool usage, humans have been natural-born cyborgs, co-evolving with mechanical devices to enhance their capacity to manipulate their surroundings. Consequently, humanity's destiny is inextricably linked to that of its auxiliary machines and devices. There may come a time when humans transition from organic entities augmented by mechanical enhancements to mechanical entities with organic remnants. To ensure clarity, we will differentiate between the destiny of humans as organic entities and their potential mechanical successors. Peter Ward expresses skepticism regarding the possibility of a catastrophe completely eradicating human life, attributing this to humanity's capacity to shield itself from detrimental conditions that could threaten other lifeforms devoid of technological safeguards. 6. Humans lack exceptional physical abilities, but possess distinct physiological requirements, such as homeostasis, a high metabolic rate, and prolonged internal gestation, rendering them highly susceptible to significant climatic alterations. Human survival will hinge on their ability to shield themselves from a progressively hostile environment. In the event of catastrophic occurrences or cataclysmic transformations, this necessitates seclusion in fortified edifices or subterranean environments, where the primary challenge is sustaining an energy supply for food cultivation. Ultimately, humanity may perceive the challenge of biological survival on Earth as excessively costly or perilous, rendering emigration to another planet an appealing alternative. Despite significant challenges, humans could create and manage an artificial environment, ultimately terraforming their new world to better suit their biological requirements. As organic entities, the disease may pose an ongoing challenge of indeterminate scale for humanity, even in an alternate realm. There is no justification to presume that microbes will diminish in response to any threat, short of sterilizing temperatures or planetary annihilation. Despite significant advancements in combating infectious diseases over the past 2 centuries, through inoculation and a century of pharmaceutical development, the peril of a global pandemic capable of decimating the human population persists. Cardiovascular diseases will likely be addressed through mechanical devices, whereas a cure for cancer and neurodegenerative diseases remains unattainable. Undoubtedly, an expanding array of carcinogens and unidentified triggers may persist in positioning these diseases as significant threats to human health. A viable alternative to combating disease and preventing biological deterioration is the transition to a mechanical life form. Mechanical entities, whether sentient machines or non-sentient robots, may be designed as cohesive, defined individuals capable of sustaining their structure and function by absorbing energy from their surroundings. Upon generating self-replicating copies from fundamental materials, they would fulfill all our criteria for life. In this context, we can refer to mechanical life. Mechanical forms of life would possess several advantages over organic forms. They would be devoid of disease, less susceptible to environmental disturbances, resilient, and energy efficient. They could be repaired with greater ease, excluding their control and cognitive systems. Managed with enhanced precision, specialized to a superior extent, and either deactivated or maintained in an active state indefinitely. Although certain characteristics may not appear advantageous from a modern human viewpoint, they could be greatly esteemed from the natural or artificial selection perspective. Under those circumstances, at what juncture would mechanical humans surpass organic humans in fitness? And what consequences would ensue for the latter? In the short term, robots possess significant potential to enhance technological capabilities, prompting organic humans to expedite their development and production. There is no reason to question that their sophistication will persist in advancing, rendering them increasingly versatile and ubiquitous. Their cognitive abilities' capacity to rival those of more intelligent species is contentious. Brains and computers approach problem-solving differently. 7. Yet, there appears to be no rationale preventing computers from attaining sufficient intelligence to program anticipation and intention. At that juncture, it may be inconsequential whether an individual thinks organically or mechanically. Should robots achieve human-level intelligence and self-replication, they may occupy the same ecological niche as humans, thus becoming direct competitors. The competitive exclusion principle is a well-established theory in biology, typically articulated as complete competitors cannot coexist. Consider two organisms occupying the same ecological niche. Natural selection will preferentially favor one organism over the other, resulting in the demise of the less favored, or its adaptation to a new ecological niche. Before achieving true competitiveness with humans, robots may be engineered by their creators to remain perpetually subservient, for example, by ensuring they are sterile or incapable of self-replication, or sufficiently distinct to preclude competition with humans. However, historical and technological trends indicate that robots will evolve to become increasingly intelligent, proficient, and sophisticated. In that case, a transition from organic to mechanical life forms may occur in the domain presently inhabited by the sole species that significantly influences its environment through technological means. Whether humans endure as biological entities or develop mechanical substitutes, insects are the organic life forms on Earth, most likely to be among the final multicellular species to vanish. Nearly 1 million insect species are documented, surpassing all other life forms. Estimates suggest that the number may be tenfold greater. They inhabit every terrestrial niche, including freshwater environments. Several species inhabit the ocean. However, their arthropod relatives, the crustaceans, shrimp, crabs, lobsters, predominate in the marine ecosystem. Insects have been documented since the early Devonian period, approximately 400 million years ago. They expanded into the numerous niches created by the proliferation of the Carboniferous forests 350 million years ago. Their robust exoskeleton, articulated appendages, diminutive size, mobility, multi-stage life cycle, and rapid reproductive capacity contribute to their resilience. They have endured at least 2 global catastrophes and remain impervious to all technological advancements humans can deploy, including the most potent toxins. Considering the extensive diversity produced by their evolution over 400 million years, they will likely adapt to confront the challenges posed by a deteriorating planet, persisting until nearly all life ceases to exist. If photosynthetic producers remain viable to sustain the food web, marine life will likely remain predominantly in a plateau state. Individual changes may occur organically. However, significant chemical alterations in the oceans or atmosphere that impact the oceans would preclude this possibility. Significant crises, such as the Permian-Triassic boundary event eradicating most contemporary animal species, can potentially induce extensive extinction. Nevertheless, representatives of the principal factions are expected to endure as they did previously. Fish have inhabited the ocean for over 400 million years, while mollusks have existed since the early Cambrian period, approximately 540 million years ago. Bony fish, bivalve mollusks, such as clams and oysters, and likely crustaceans are expected to endure until the oceans evaporate. Peter Ward's forecast for the future of animal life predicts that humans, domesticated animals, small cohabiting species and birds, will comprise the predominant terrestrial vertebrates likely to endure the ongoing mass extinction. Domesticated animals will persist due to technological advancements allowing them to withstand all but the most severe environmental adversities. Birds serve as the vertebrate counterparts to insects. Their continued success is contingent upon their diversity and adaptability, provided that plants persist at the foundation of their food chain. Plants will adapt, as they consistently have, to evolving conditions. Their energy source will only become more plentiful as the sun intensifies with age. As the planet experiences significant warming and freshwater resources diminish, the continental landmasses will progressively become arid, retaining moisture solely at the poles, and ultimately, even that will be lost. Upon the extinction of terrestrial plant life, all animal and fungal species will perish. Microbes will migrate underground, where they can persist as long as they can retain moisture and produce sustenance through methods other than photosynthesis. Multicellular organisms began to thrive on Earth over 500 million years ago, integrating into the microbial biosphere for at least 3 billion years, resulting in the most extensive biodiversity in the solar system. Life on Earth exhibited considerable diversity and resilience, enabling it to endure multiple global catastrophes and successive ice ages. Taxonomically diverse groups such as insects, mollusks, birds, and fish, governed by Darwinian evolution, will likely have some representatives persist as long as plant life endures and the planet remains habitable. Through technology, humans, their progeny, or their mechanical successors, and select domesticated species under their protection, may persist until the planet becomes uninhabitable unless they depart beforehand. Predicting the appearance of the biosphere as it nears a critical survival threshold is exceedingly challenging. We are currently experiencing a period of extinction, primarily propelled by humanity's quest for technological dominance over the environment and its destiny. Genetic engineering is currently modifying the trajectory of evolution via intentional selection. This trend is expected to persist, yielding highly unpredictable and potentially unintended outcomes. Utilizing the historical trajectory and destiny of life on Earth as a paradigm, we can extrapolate the fate of life in other contexts. Upon its emergence, life will adapt with minimal alteration to the existing planetary conditions. After altering those conditions, the evolution engine will activate to modify the biosphere. Significant habitat fragmentation and diverse environments conducive to liquid-borne chemistry will foster biodiversity, enhancing the likelihood of survival for certain life forms as long as the planetary body endures. As conditions become increasingly restrictive, the number of survivors will diminish. In the presence of environmental stability, even if it is exceedingly harsh and restrictive, some life, though not particularly diverse, will endure. In environments conducive to advancing intelligence and technology, the capacity to modify or mitigate natural climate trajectories and address other natural disasters will exist. The potential for transitioning from organic to mechanical life forms must be acknowledged. When beings in such a world acquire the capability to traverse space, departing for another world becomes a viable option for both organic and mechanical entities possessing the necessary means. Upon the emergence of life, it exhibits extraordinary resilience and tenacity. Stabilizing selection predominates over directional selection in the short term. maintaining organisms' optimal fitness for their environments. Most life forms exist in a plateau phase of evolution at any given moment. In the long term, as environments shift or disasters occur, evolutionary mechanisms cannot adapt swiftly to the changed conditions, leading to extinction. In exceptional instances, novel discoveries or environmental alterations can considerably benefit a previously insignificant trait. This can induce a significant alteration in evolution and establish a new benchmark from which descendant forms may develop. Our solar system offers a diverse array of celestial bodies that are probable in any solar system, although the complete spectrum of these worlds remains unknown. It is hoped that it serves as a valuable proxy for the likelihood of extraterrestrial life in the universe. Carbon-based, aqueous life forms possess distinct biochemical and physicochemical advantages compared to alternative building blocks and solvents. Assuming conservatively that this is the sole viable form of life, we would anticipate discovering life or evidence of former life on at least 3 of the 4 terrestrial planets: Venus, Earth, and Mars, and on the moons of at least 3 of the 4 gas giants: Jupiter, Saturn, and Uranus. Consequently, we deduce that historical and contemporary life has been prevalent. Under this conservative assumption, we are confident that complex macroorganisms emerged in only one instance. They may have existed on Venus, Mars, and Earth at one point. However, they are likely now extinct and confined to caves or subterranean reservoirs on Mars. A potentially intricate ecosystem may exist within the subsurface oceans of icy satellites, specifically Europa and potentially Enceladus. Regardless of the size or complexity organisms may have attained in their history, they are currently entirely isolated from every other celestial body in our solar system. Should a more permissive assumption be adopted regarding the conditions conducive to the emergence of life, the exotic scenario, the potential worlds currently existing within our solar system must be expanded to encompass Titan and Triton. This broadens the spectrum of potential habitats for life across the cosmos. Yet it does not alter the essential reality that, in most instances, life will be confined to subsurface environments and is likely to be small or microbial in scale. Once life emerges in a particular world, particularly where the biosphere is diverse, it is likely to reflect the planet's history, remaining stable as long as the environments are consistent and adapting to the challenges posed by new environments as they arise. Life is expected to endure as long as the environmental conditions permit any form of existence. Ultimately, as the central stars of solar systems extinguish and subsequently perish in a final explosive release of energy, the proximal planets will be incinerated, while the distant ones will be deprived of the life-sustaining energy supplied by their sun. The extinction of life on affected worlds is highly probable and represents the ultimate fate of life in all locations. The emergence of intricate ecosystems inhabited by substantial organisms possessing considerable information processing capabilities, termed intelligence, seems infrequent. The advancement of technology is even rarer. However, it is highly probable that such occurrences have transpired and are currently unfolding in remote regions of the universe. The emergence of technology alters the trajectory of life's evolution. Technology significantly impacts the environment and can produce machines that replicate the fundamental capabilities of their biological progenitors. This engenders the potential for competition and even substitution. In realms where intelligent organic and potentially mechanical life forms may develop, the prospect of space travel offers a viable alternative to extinction.